This meeting is being recorded.
Hello, everyone. I'm Professor Anderson Rocha. I'm here at the Institute of Computing, University of Campinas, Brazil. And we are glad today to have the presence of Professor Romain Giot. Professor Romain Giot is from the University of Bordeaux. He is going to talk to us about explainable deep learning. Okay, so this talk is being recorded and it will be available over our Record AI website and a YouTube channel later on. So normally we are going to have about 1 hour of presentation and then 20 minutes, about 20 minutes for questions. So I hope that you are hearing us well. So if you can confirm over chat, if you can hear me well, please someone let me know. And then I will head to Professor Romain Giot for his start. Okay, it's okay. All good. Thanks a lot. So Professor Romain, thank you for joining us today. And the stage is all yours. Please go ahead.
Okay, thanks. So I'm Romain Giot from the University of Bordeaux, and I will present you something related to explainable deep learning. So feel free to interrupt me during the presentation if I need to provide more details. Okay? No need to wait till the end of the presentation. So I will first start by some generalities about deep learning. Since 2012, there is a revival of deep learning. It's not a new technology, it dates from several decades, but scientific and industry are using more since 2012. And why? Because of several reasons. For example, we have access to more computing resources, such as the GPUs. We have access to more data, thanks to big data infrastructures. And there is also a nice thing, when you are using deep neural networks, you do not have to do any more manual feature extractions. So it means that people that do not have the knowledge of the data can use such kind of method, whereas before you had to really have a strong knowledge of your data. It's used in several applications and use cases, for example, with segmentation, classification, instance segmentation, data generation, dimension reduction. There are lots and lots of use cases, and we can find more every day. And it is also almost data agnostic. It means that if you are able to manipulate a tensor, such as an image, a video, you can use deep neural networks, but you can also use them with graph data, with business structure data, with text, and lots of other kind of data. However, deep learning suffers several limitations. I have classified them in three kinds of limitations: the technical limitations, the legal limitations, and the acceptance limitations. Regarding the technical limitations, it is known that deep neural networks are highly sensitive to bias, and they can also be attacked in operational environment. So when they are sensitive to bias, it means that a model that has been created in a research lab can be totally inefficient in a practical scenario, because the dataset that has been used is not representative of what happens in real life. And regarding the attack, if you look at this stop sign, a human person clearly say that it is a stop sign. I do not know if you have the same in Brazil, but in Europe, they look like that. And when we look at that, we know that it is a stop sign. However, you can see that there are some patches on the image, and the deep neural network that has been trained to recognize the signs do not recognize a stop sign anymore. It recognizes a limitation of 50 kilometers. Okay, so the deep neural network can do such kind of mistakes that we will never do. We need to have masses of data to learn them. Okay, for huge models, public research labs are not able to learn them. They do not have the computing resources, and they do not have the money to pay the electricity bill to to learn them. So it's a big issue. And there is a black box effect. Models are often oversized in comparison to what is needed in their use. Okay? Lots of time, the models are very complicated and we do not really know what happens inside. I will go quickly for the legal limitation, but in Europe and in France, we have some laws that request us to provide explanation when an algorithm has taken some decision. And I've seen that in Brazil, you have the LGPD law, and I have seen this sentence. Whenever requested to do so, the controller shall provide clear and adequate information regarding the criteria and procedures used for an automated decision subject to commercial and industrial secrecy. And I understand that you also need explanation by looking at this sentence. And the third issue is the acceptance limitation. Due to this black box effect, it's too much complicated to understand what really happens inside. And because of that, people may do not agree to use such kind of model in specific scenario. For example, in aeronautics, you need to have certified software. And today, we are not able to certify deep neural networks because we have no proven guarantee of their output. And so it could limit their adoption for health, safety, autonomous vehicle, etc. It's not really true because in autonomous vehicles, they are using deep neural method, but I do not trust really them. So what are the solutions to these issues? We have tons of solutions regarding the technical issues by improving the learning process, by improving the data collection, the way of labeling data, etc., etc. I will not go on more because it's not the purpose of the talk. For the need of data, we are all using a pre-trained model and specializing them on our smaller data sets. But there are also kind of architecture that are able to learn with fewer data, like the one-shot learning, Siamese network, such kind of architecture. And for the black box effects, of course, there is explainable deep learning. Regarding the legal limits, once again, the solution is the explainable deep learning. And regarding the acceptance limits, once again, one solution is explainable deep learning. So what is explainable deep learning? Explainable deep learning will be a set of tools that will allow us to go beyond the standard evaluation method. Today, when you're applying machine learning algorithm, you are able to evaluate them. You can use some evaluation metrics and compare the evaluation metrics. And thanks from that, you can know if the model is efficient or not, but you do not know why it is efficient or not. You have the ROC curves, you have the confusion matrices, you have tons of tools to evaluate them. It just gives an idea of the performance, not more. With explainable deep learning, we will try to explain the reasons, and we will provide, we have tools to do that, and the explanations can be at different levels. It can be at the level of the model, it can be at the level of a sample, it can be at the level of a data set. And in the explainability area, we can find two different kinds of explainabilities. What is named intrinsic explainable models. So it means that the model does the explanation by itself. And what is called post-hoc analysis, where you are generating the explanation afterwards. So we will see these two kind of things. So to use self-interpretable model can be a solution to bring explainability. What we can do is that we can build a self-explainable model that is not a deep learning model from a deep learning model. It means that we can learn a simple model that we are able to explain and that tries to mimic a complex deep neural networks. And then we will not try to explain the deep neural network, but we will try to explain the simple model. In the literature, we name that a student model when we are training a simple model. And which model in the literature are able to be self-explainable? We can find the associational rules. I do not achieve to say this word in English. The trees, the decision trees, and the linear classifiers when you have few features. And another path is to create interpretable deep learning. It means that we will modify the training procedure. We will add specific modules inside a deep neural network in order to allow the deep neural network to produce explanation at the same time that it produces its prediction. So when we have been able to represent a deep neural network with rules, how do we present them to the user? One simple way is just to print the rules on screen and let the user read them. The problem is that it does not scale when there are lots of rules. You will have a huge list that you have to interpret by yourself. When you are manipulating trees, decision trees, you can draw this decision tree, and it helps to understand what happened. Once again, when the tree is huge, you are unable to make a clear representation. Here, it is a small tree, and it takes already lots of spaces. You have lots of information on screen. Even with a small tree, it can be complicated to understand. Regarding interpretable deep neural networks, there are few works in the literature that do that, but they stick on the same kind of things. What they do is that they try to make, when the network is training, they try to learn concepts at the same time. And when the network is doing its prediction, the network must explain which concepts is at the basis of the prediction. But the problem is that these concepts are automatically learned, and we may be unable to name them. Maybe this concept has no meaning for us. Okay. Do you have a question about this intrinsic method? Or I will go to post-hoc analysis. So post-hoc analysis corresponds to most works in the literature. It's probably what you are already doing if you are doing some kind of explanation. We can share them in two main approaches. The local approaches, that is probably the one that you are using, where you are trying to make an explanation for a specific sample. And you have the global approaches when you're trying to do more general explanations for the whole data set or for the model, but without being specific to a specific sample. And then we have listed various ways of doing that: feature attribution, explanation by examples, counterfactuals, learned features, and model behavior. So I will show you some examples for each of them. Another thing to know is that explainable deep learning has been mainly studied by two communities: the machine learning community and the information visualization community. And the choices made by these two communities are quite different. So at the beginning of the talk, I will mainly discuss the proposal of the machine learning community, and at the end of the information visualization community. And they do not try to address the same problems. Machine learning community is more with local approaches, whereas information visualization is more on global approaches. So maybe you have already used individual conditional expectation method. But this is a method that is mainly used for tabular data when there are few features available. And the idea is to modify the samples and check how the model behaves on the changes. So here we want to check how the edge feature impacts the prediction of a conserve of this specific data set. The edge feature goes from 0 to 80. And what has been done is that each sample of the data set has been modified on its edge feature. each line represents a sample, and each line represents a sample. And for each sample, we have progressively modified each edge feature to give it the whole interval. And so what we can see is that when we are reaching, maybe it's 45 here, when we are reaching the age of 45, the probability of having a concert increase. So by looking at that, we can say that the age is an important factor to predict if we have a concert. But it does not scale when you have lots of features. It does not work well when features are correlating. The partial dependency plot is exactly the same thing, except that instead of showing all the samples, they have been aggregated, and we show the mean. And so this way, sorry, we see the tendencies. After a certain age, the probability increase. Accumulated local effect plot is a kind of similar method. Instead of showing the final prediction, it will show a kind of difference between what is expected and what is obtained. It has the same kind of limitation. It's really similar. Permutation feature importance also works with tabular data. And what is done here is, if you consider your dataset as a big table where each line is a sample, each column is a feature, this method will do for each feature a shuffling of the columns. So it will set the value of another sample to another sample, and it compares the difference of errors between the normal dataset and the modified dataset. Okay. And so for this specific example, we see that the four or five first features on the top are the most important to help for the decision. Okay. But the problem of all this method is that it works with small datasets. Lime, that you have probably used already, is a method that has been designed to explain for images, for text, and for tabular data. I will not go into the details, but I will just present it quickly. Something I have forgotten to say is that all the methods I have presented before, and Lime included, works with black boxes. It means that we do not have to access to the code or the data of the model, just its output. Okay. And when working on images, if I explain quickly Lime, it will split your input image with superpixels, and it will check which superpixels highly vote for the class of interest or highly vote against the class of interest. So it is one of the first methods that allow to scale very well with images. But there is a problem in the method. It's something that is quite iterative, and at some point you have to remove information inside the image. You have to remove superpixels, and the fact of removing superpixels is not really well defined. There are many ways of doing it. What has been chosen in Lime is to replace the superpixel by the average value of each pixel, but it's maybe not the best method. And there is randomness in the method, so each time you launch it, you may obtain different results. Rise does not suffer of this issue, and it's far more simple. It is a method that tries to generate something that we call a heat map that represents the importance of each pixel in the image for the final classification. And this is done quite easily by generating some random masks that will hide some pixels, multiplying this mask with the image to remove the information. So here there is still the aspect of information removal in the method. And then to predict the modified image with the classifier and see how it changes the probability of belonging to a class. And the heat map is just built by doing a weighting sum of this mask where the weight is the probability of being of the class of interest. So this is a very easy method to implement, quite fast to execute. And the problem is that it is limited to image classification, but it works quite well. And the resolution of the heatmap is high. It's the same as the resolution of the input image. So these were methods for black box approaches. It works with anything. Here, I present the method that we name class activation mapping based, so CAM, GradCAM, that you have probably used. These methods are for white box. We need to have access to the inner detail of the model to compute them. For CAM, it is even worse. You need to modify your model to add something specific inside to be able to compute. GradCAM does not suffer of this issue, but it is quite low to compute because you need to compute the gradients. And this method relies on the activation. They use the activation at the latest convolutional layer in order to generate the heatmap that say which part of the image is important. So this time the resolution is quite low because we have the resolution of the last convolutional layer. And then to obtain the heatmap on the full picture, we apply an upsampling method, but still there is few information at the beginning. So I'm pretty sure that you have already used GradCAM because we can say that it is one of the state of the art of the method. There is another one, but is also another state of the art, that is layer-wise relevance propagation, LRP. The advantage of this method is that the resolution, once again, is to generate heatmap, so which pixel is of interest. Of course, it works also with tabulated data. But the advantage of this method in comparison to GradCAM is that the resolution of the explanation is the same as the resolution of the image. It works by propagating some information from the end of the network, from the output of the network to the input of the network, okay, by computing some rules. And these rules depend on the layers. You have different rules per kind of layers. Sadly, there are some kind of layers that do not have rules, so you cannot compute LRP for them. And also, sadly, for a specific layer, you can use several rules. So to use LRP is quite complicated because you need to parameterize lots of things. In my lab, we have created a method that is named FEM, and that relies on the same principle that what we have said. We use the activation of the last convolutional network. We make some kind of computation that makes sense for us, and it provides a heatmap. But when we have evaluated our method against GradCAM, we have discovered that our method produces heatmaps that looks more like what humans are looking at images. To make this evaluation, we have used gaze density fixation heatmaps. So it means we have used data collected from human by checking what they are looking at the image, okay? and generating a heatmap from that.
You use eye trackers?
Yeah. Several datasets. Some datasets with eye trackers, and another dataset where it is a bit weak. It's the people that use the mouse to show where they're looking at. Mm-hmm. But our results are more correlated to that. Once again, the resolution is quite low because we are using the latest convolutional layer, but you are able to improve the resolution by computing an explanation map at different layers and merging them. The information provided at different layers differ. So we have an even better representation. So what I have presented now was feature attribution, and I'm pretty sure that this is the only thing that you are using when you're trying to do explainability, because in the literature it's maybe 9 papers out of 10 that is like that. The problem is that such kind of method has several issues. It has been shown that if we modify a network and we use such kind of method, it may not impact the explanation. So it makes no sense. If you modify the network, the explanation should change. And there are some methods that are insensitive to that. So we cannot trust them. It has also been shown that you can create a kind of forgery of explanation. There are some methods that are able to slightly modify the input image to be sure that the explanation will be what the attacker wants to be and not what is the real explanation. So once again, because of that, I do not know if we can trust such kind of method. Another category of explanation is what we have named learned features. And the very first method that corresponds to this category is class score maximization. So it's work that has 6 years. It was really interesting at that moment. Today, we do not use that anymore. It works with white boxes, and it is a global approach. So we do not focus on a specific sample. What happened here is that we want to generate an artificial image that will produce an output in the network with a high probability of being a target class. So for example, here we have generated an artificial image that is highly probable to be a lemon. Okay, so we do not see at all a lemon inside that. We do not even see something that looks like a lemon, but we can observe some kind of patterns that appear in a lemon. Okay, so such kind of method has been used to get the patterns and allow human to try to infer knowledge from these patterns. But it's clearly results out of distribution. It does not look like at all to a lemon. A few years ago, such kind of method has been improved to produce more realistic images. They still suffer of out of distribution issues, but we better understand what kind of patterns are treating by some specific filters or by some specific layers or by an aggregation of filters. Okay, I do not know if you know this site distill.pub. So I think it's close in one or 2 years. But before, they were providing very interesting information related to explainability. So what we have seen now for this category of learned features is that we are able to generate images that are more or less realistic, that show patterns of interest of the network, but they are more or less realistic than true. So there has been another method that has been created to generate artificial images that really look the object of interest. And how they are doing that, the approach uses 2 things. The network that we want to explain. So this is a network that takes as input an image and that makes a classification at the end. And we want to understand, for example, what is a shoe for this network. And we will generate, once again, artificial shoe. But before, there is an optimization process inside. But before, we were trying to optimize the pixel of an image. Whereas now, we are trying to optimize a very small vector. And this very small vector will be transformed as an image of the shoe with a generator network, a generative network. So instead of optimizing a huge thing, we are optimizing a very small thing, and it allows to generate the artificial images that you can see here. Still, they're a bit different than the real object that they're representing, but they look more like the real object than the previous method that I have presented to you. So this is an old paper. I have not checked if today we are doing better. There is a paper that is named Network Dissection, but I have read it so long ago that I do not exactly remember how it works. But what it tries to do, it tries to make a mapping between concepts and filters. And it will try to say, these filters are trying to detect such concepts. and the concept has to be provided by human before. I will pass this one, otherwise I will be too slow. I will pass this one also. So now I will talk of another category. This other category is explanation by example. We want to try to explain a model by showing some example, and from them the human will infer some knowledge to understand what happened. One first way that works with black box, and that is a global approach, is the detection of influential instances. What are influential instances? These are samples from the training data set that have a strong impact on the quality of the model. If we remove them from the training data set, the performance will decrease. So these samples are really important. And if we are able to get them, maybe we can understand why they are important for the network. I have not said too much in the beginning of the presentation, but each time with the explanation, there is still a huge human work to do by thinking about what it is seeing to get the explanation. Anchors, maybe you have used anchors. It is a method that is that comes from the creator of Line, and we can see that as a method that will take a sample and that will try to remove everything that is useless to show the minimal things needed to be used by the model to make its decision. So, for example, when it is looking at text, it will search support of the text that really supports the decision. When it is looking at images, it will look at support of the image that really explain that are really useful for the model. But it is a very complex method that is really computationally intensive. And I do not know if it is used a lot. Counterfactuals, maybe you have heard of counterfactuals. Counterfactuals are samples that are used to explain another sample. They are close to it, so not too much different, but they belong to another class. So for example, in a bank, we can say, you have this data, I cannot give you a loan. What do you need to change to allow me to provide you a loan? The counterfactual is the modification to allow you to have a loan. So there are different strategies to get this counterfactual. There are some methods that are using some optimization things to get in the training data a sample that is from another class, but that is quite close. Or there are other methods that try to generate artificial examples to do that. Of course, when you're generating information, you suffer yet of out-of-distribution issues. There are some criteria to say if we are a good counterfactual or not. We need to reduce the prolixity. It means that the counterfactual need to be as close as possible than the example we want to explain. Few changes must be computed. We need sparsity. It means that in the feature space, as few as possible features have been modified in order to generate the counterfactual. And the plausibility, it means that the generated counterfactuals need to be in the domain. It's once again related to the out-of-distribution issue. The counterfactual need to be realistic. There is another category that is named model behavior, where we want to understand what kind of computations the model is doing. I have not found lots of examples in the machine learning literature. This one is a bit borderline. It's a generative model that is modified in such a way to force him to generate data differently as the person that has modified it wanted to. And to be able to do such kind of modification, you have to understand what happened inside the generator to make modifications inside at the right place. So if you look at this paper, you will see how they handle this issue. But most works related to this model behavior category come from the information visualization community. So I will explain them later, because you need to use visual analytics to really do that. So what is information visualization? Visualization can be described as a mapping of data to visual form that supports human interaction in a workspace for visual sense making. So this is the definition. It's a bit impossible to understand. So I will re-explain it quite differently. When you are doing visual analytics, what you have is you have data. This data, you will create a visualization on it, and then a human will look at this visualization. When the human will look at this visualization, he will make some kind of interpretation and build some knowledge based on its interpretation. And when the human has obtained the knowledge, he will want to dig more into the data and interact with it. I don't know, for example, to filter things, to zoom in things. He will do various kind of interaction. And this interaction will generate new visualization. And from this new visualization, he will make new interpretation, bring new knowledge, and so on, and so on, and so on. So there is this loop of interaction with the data to build the knowledge. And information visualization is quite short in the human history, because almost everything has been invented at the end of the 18th century, or the 18th century. Pie chart, histograms, area chart, everything has been created at this moment. And it has been described precisely in 1967 by a book of Jacques Bertin that describes how we create visualization. So it's really recent in the history. Today, computing resources allow to design interactive and complex visualization, but there are still some rules to respect. When you're visualizing things, you will use various encoding related to size, shapes, orientation, and so on to make your representation. For example, have you already used t-SNE to reduce a huge dimensional data set and project them in two-dimensional data set and show them on screen? Here, there are several encodings that are used. The position of the point, that is the result of t-SNE, but there is the color, probably the color of the class of interest, and eventually the shape, that can depend on other factors. Okay? But the problem is that the quality of these encodings depend on the kind of data that you are manipulating. Position is always a good encoding, but for example, length is a good encoding when you're manipulating quantitative data, but it is a very bad encoding when you're using ordinal data. And so you have to take care of such kind of things when you're designing visualization. In visualization, you have two families: scientific visualization that concerns concrete data. You have real data from the real world, and then you want to depict them for a human to understand this data. You have not a lot of choices because it depends a lot of the kind of data that you are manipulating. In the opposite, what we are doing there is information visualization that concerns concrete data, abstract data. As this data is abstract, you have many ways to represent them. So we have lots of tools, of visualization tools, to represent the data. And the difficulty will be to choose the best encoding for specific data. I have not talked enough of interaction. I have, but interaction is really important with the rest of the talk. So at the beginning of the talk, I have shown to you how we could look at association rules by printing them on the screen. Okay? But there are visual analytics researchers that have created visual analytic tools to show them in a different way that allow us to better understand them. Rule matrix is one tool of this kind. So what can we say when we are using visual analytic tools? It will bring us more knowledge than the static information that can be shown, but it comes at a cost. You have to learn how to use them. Okay, it takes time to learn how to use such kind of tools, to understand what information is shown at which place, which kind of interaction can we do. It takes time. But when you have learned how to use such kind of things, you acquire knowledge of better quality. Okay, so this rule matrix tool that looks like quite complicated, and I cannot explain to you quickly how it works, but allows to better understand association rules. You have probably manipulated random forests. Random forests are composed of lots of trees. Each tree is a complex thing. When you have tons of trees, it's even more complex. And this tool allows to better understand what happened in the forest. So you can be able to learn a student forest from a deep neural network and visualize the student forest with such kind of tool to better understand what the deep neural network is doing. You have probably used confusion matrices to compare the prediction depending on the classes, and confusion wheel is another way to represent the confusion matrices by providing more details, and we better understand the relations between the samples and the classes. Once again, it takes time to learn how to read such kind of things, but when you're able to read such kind of things, it provides more information than the standard confusion matrix. Okay. So these last slides were quite general in the machine learning. Now it will be more specific for deep learning. Often we want to get an idea of the architecture of the network. Okay, it's necessary to have a representation of the architecture to understand what are the technical aspects of the network. It's not necessary. It's not sufficient, but it's necessary. And in the literature, we can find two kinds of methods to depict a network. Usually, we are using a graph-based representation where each node represents a module inside the network, and there are links to show that this node needs information by other nodes to be computed. So on the left, it's a graph that is generated by TensorFlow when you want to look at your network. So it can be huge. It can take a lot of spaces. So you need to zoom in, zoom out to really see what happens. And on the right, it's totally the opposite. It is a method that has been dedicated to create pictures to put in papers. So you provide the code of your network, and this code is transformed with this compact representation compact enough to be put in a scientific paper to represent your network. So this is the first step. Visualize the architecture of the network. Another thing to know is that the expectation of users of such kind of tool differs. On the left, I have put a website, maybe you know it. It's named Tensorflow Playground. Its aim is to be used by non-experts that want to learn how works a multi-layer perception. So they can create by themselves their network, and they can feed it with some data, the data or XY data, and click on a button to make the training start, and they will see how the classification evolve over the training. By using such kind of tool, you can learn quite fastly and easily how it works. On the right, it's totally the opposite. It's a tool that is dedicated to medical doctor that analyze sleep state of their patient. And this tool has been created to help them to detect classification issues with a deep neural network that they could use in their work. So the interface is far more complicated. Once again, you need a lot of time to learn how to use it, but it provides interesting information. But it is dedicated especially for this specific application. We cannot use this tool to understand a CNN that recognizes dogs and cats. Okay? It does not fit at all for such kind of network. In the literature, local approaches and global approaches are studied differently. There are people that create methods that are local, people that create methods that are global. And I'm pretty sure that it is interesting to mix them, especially with visual analytic tools, where you create a first representation that is global, and then when you're interacting with your visualization, you can obtain local details on demand. So I'd like to work in this direction in the future. Visual analytics can also help to build a simpler model. To build simpler model, you need to understand what happened during the training. You need to understand what happened inside the network. So it's yet related to explainability. And here there are two examples of tools that have been designed on this purpose. They help the user to understand when and how to simplify the model, and it has been proven to be efficient. Okay, I said at the beginning of the talk, most of the time we are using models that are far way too complex in comparison to what we are asking to them. We should be able to use almost always the simpler models. You also need to really understand your data when you want to explain a model, because the performances of the model depend on the training data. Okay, if you have bias in your training data, it's normal that your model does not perform well. So the tool on the left, is a tool that we have done to help people to fix labeling issues in their data. It's something that we have done with a company where they pay people to label image data. And in their process, once the image data has been labeled, they have a verification process to verify if the labeling is correct. And this verification process takes twice much time than the labeling process. And with such kind of tool that is able to detect possible mistakes and that is able to make fixes proposition, it speeds up such kind of correction. And on the right, it's a tool that has been made to detect bias in the data set. So balancing issues with features or with classes and things like that, that could explain why the model does not answer properly. I will quickly show a few works that we have done in my lab. For example, the picture on the top left, it's a global approach that we have used to try to understand how the data, the training data, is handled by the network. What we have done is that each layer of the network is represented by an axis. So here it is a layer, and here it is something that simulates the confusion matrix. What we have done is that for each layer, we have retrieved the activation values of all the training samples. Okay. Then we have applied a clustering algorithm on these activation values. Thanks to that, we obtain partitions of activation values, and in each partition, we have activation values that are quite similar. So we have created groups of samples that are quite similar at this specific layer in the network. Okay. Then we represent each partition with a rectangle in its layer column. But each partition contains samples that could belong to different ground truths. Okay. So inside this rectangle that represents all the partition, we have added other rectangle that corresponds to a specific ground truth inside this partition. So for example, for this partition here, we have a lot of green color, so a lot of 3 and a bit of 5. So it means that at this layer, there are several 5 and several 3 and few 5 that have similar activations. We do that for each of. We draw a line between all over the network. In fact, we do not do that for all samples, but for all groups of similar samples. But that's the point. So thanks to that, we can see flows of data over the network. When we see splits, it means that samples that were quite similar at a specific layer are considered to be different in the next layer. And when we see merges, it means that samples that were considered dissimilar in a previous layer are now considered similar in the next layer. Okay, and thanks to that, we are able to see how fast, depending on the topology, not the time, how fast the network is learning to differentiate the data. And in the opposite, we have also used it to detect networks that are too much complicated, because at the beginning they start to be similar and then they diverge, and after they start once again. And when we see such kind of patterns, we understand that the network is too much complex.
This is a nice way of seeing the learning process.
Yeah.
But you can also get now in the tests, you can get some individuals, some tests feature vectors, then you can see the flow of that particular feature vector. And suppose that you have the traditional flow for the green. So the green is class 2, I think.
It's free. It's
class 3. So the normal pathway, if we connect what you did here with neuroscience, it's what they call pathways, a neural pathway. So you are kind of doing the neural pathway. So the 3 has the green one. So now suppose that you get the number 3, but you put it there and it says 4. Why? Then when you put and you follow the flow of the number 4, you're going to see where it diverges. So it's a nice way of visualizing what's happening.
We have stopped this work quite early, so we have not done everything that we wanted to do. But of course, such kind of thing is on the good direction. Before I have talked to you about t-SNE. t-SNE is a really bad way of doing data dimension to produce scatter plots. There are several issues. One of them is the difficulty of configuring the perplexity parameter. Depending on it, the visual result can be totally different. And another issue is that you can have lots of overplots. It means that you can have lots of points that have similar coordinates. And when they are drawn on screen, you do not know that. For example, here there is a small brown area, and here there is this big blue area. Maybe there are more samples inside this small brown area. It's just that they are just aggregated at the same coordinates. And we cannot see that with t-SNE. So we are trying in my team to create something that we name grid-based representation, where overplots is impossible because we ensure that each information has its own pixel on screen to be represented. And there is no hole in the representation because we put everything in a grid. So it's very compact and we can show lots of information close together. And we will use such kind of thing to improve what I have shown to you before. The thing with the flow is a global approach, and we will try to meet this global approach with this local approach that look at the samples individually. We have also created a tool to simplify deep neural networks. So it helps us to understand which part is superfluous, which filters are not useful to individually remove the filters. And of course, we have worked on several feature attribution methods. So what I see for the future, I think that verbalization should help for understanding. Today, people are, whether they are from information visualization or from machine learning community, people are creating images. And then humans have to read these images and to infer knowledge from these images. For example, think about the feature attribution method, GradCam. You have a picture of a cat and a dog, and you say to GradCam, why you said that it is a dog, and you have the highest color of the heat map around the dog. So we just know that it is these pixels that are interesting, but we do not know why these pixels are interesting. We do not know if it is because of, I do not know, color information, shape information. We have no idea. It just said that it is here, that's all. It's not enough for me. And I'm pretty sure that to use verbalization would avoid such kind of ambiguity. If you are able to generate a sentence that is really clear, really explicit, and that say, it is that because of that, and that, and that, we will better explain. In the literature, you have the intrinsic method and the post-hoc method. And once again, I think that we should mix them. We should be able to create a mix of them. Another thing is that often we have representations that are too complex or representations that are too simple. And I think that we should work on kind of adaptive representation that will change the way of representing the data depending on the user. For an expert, it can be more complex. And for standard end user, it could be more simple, even if it lies a bit. We are always lying when we are doing representation. So the aim is to lie as less as possible. Collaborations between machine learning and visualization communities needs to be strengthened. And today, works are done by machine learning guys or by information visualization guys. There are few papers where people from both communities have worked together. And when it will happen, it will improve the quality of the tools. So data experts, model experts, and data visualization experts need to work together, and call for papers should be open for both communities. And linked to what I said before, semantic information has to be provided to the explanation. As I said, feature importance doesn't bring enough information. We need the semantic behind that. And deciders need to take decisions based on semantics, because we better understand when we have the semantic of the explanation. And also the explanation needs to be trustworthy. Today, I cannot say that I trust all of them. We have nice explanation, but I do not know if I can say that, if we can trust them.
You don't know if you understand the explanation.
Yeah. And that's all. I'm ready to answer to your questions.
Just a minute. Let me open the camera here too. And I will ask you, if you have questions, please to come up front because of the mic here.
Okay, no problem. So you can start to come.
Let me also put myself here.
try to.
All right, so guys, thanks, Professor Romain, for the talk. I will ask you kindly if you can share these slides with us later so I can send to people that registered for this talk. I remind everyone that the talk is also recorded and will be available at our website, record.ai. I will go now for the round of questions. I already have one here from Dr. Aurea. If you have questions and you are in the audience, the e-audience, the Zoom one, please type your questions here or let me know that you want to open your mic and we can go over with the mic as well. For now, by default, the mic is turned off. So if you want to type your question, please go ahead. If you want to open your mic, let me know over chat and I can open it, okay? So Aurea, please go ahead with your question.
Thank you very much for this talk, Professor. And I have a comment. I think we have a problem with Disney because the classical visualizations of Disney are based on scatter plots, and scatter plots has a lot of problems. I was reading, this solution of having one data point as a pixel is a great solution for that. But when we talk with big data, maybe it's not enough. I was reading and having some combination of other visualizations for the visualizations with are based on scatter plots, like for instance combining graph splaying, which is based on Gaussians, with Disney in order to try to represent more data for that for those regions where we have a lot of points. So it's just a comment. Maybe we could have another kinds of visualizations for these visualizations which are based on scatter plots, which has a lot of problems.
So first, for the grid-based visualization, we have lots of pixels on the screen. 800 multiplied by 600, it's a lot.
It's a lot.
It's a lot. So you can represent a lot of information. And regarding the scatter plot, at some point, maybe you have to make the choice to not represent all the data. So you have to make some kind of aggregation and to allow the users to interact with the visualization in order to open aggregated areas and see more what happens here. And you have also to think about other ways to represent that on screen in order to let the user really understand that there are lots of data here. So for example, by showing the probability density function of the data, a heat map, a heat map under the scatter plot to understand that here there are lots of points, so you have to zoom.
Yes. It's a good point. And also, there are a lot of multidimensional projects which are based on that idea of having a hierarchical solution. And yes. Well, thank you.
Antonio.
Thank you, Professor Romain, for the amazing talk. Interesting to see how these two different communities see the problem. It's a feeling that I have. It's nice to see you saying that, because I have a question about the techniques that you showed about using training examples to explain a model. The first question is, I understand that these techniques, they show which training examples are more important or not for a model behavior, but they only show the ranking of these training examples, or they try to aggregate. Because I imagine a big data set where you have millions of samples. Did they only rank, or do these works they also try to aggregate the results to give some more meaningful and not so granularity.
Okay, just to be sure to answer properly, is there a slide where I can?
Yes, the one about selecting the training examples that will influence the learning model.
Ah, you were talking about that?
Yeah. Does do the works that do the papers that the group that work with this kind of techniques, they only rank the training samples about to explain the model, or do they also aggregate the samples to give a better not so?
I have not read lots of information about it, but in my opinion, they only rank.
Okay.
Maybe there are work that do more,
Okay.
but I do not know that.
And the last question is about when we are talking about sensitive context like health or court, for example. I see that some techniques try to explain the using elements of the sample that were about to be predicted, and some others like these works explaining which training examples were more influential for the decision. Do you think that these last techniques that uses the training examples to explain the prediction of another sample, does these techniques have future? Are they
Promising.
useful, promising for this context, or maybe these techniques are helpful to improve the model, but not to be used as an explanation for court or health?
I do not really know, but there is a strong limitation in the quality of the training data set. If it is not enough representative, you will never be able to get the right example. So first thing is to have the right data set. And then in an operational scenario, I'm pretty sure that medical doctors would prefer to look at pictures of things than abstract representation. So using this example will always be important. As soon as you have a representation of the data, because we have problem, you have no real representation. If it is just a vector of values that we do not know exactly what are these values. But when we are using images, I'm pretty sure that you still have to show the
elements of the image to be predicted and not training examples that led to the prediction, right?
I have not well understood.
I mean, in this sensitive context, do you think it's better to explain by the elements of the sample that were predicted, that were about to be predicted, and not training samples that were used in the training phase?
You mean to show subparts? You mean to extract information inside? Is it what you're meaning? To instead of showing a complete example, just to showing the small part inside that was of interest?
No.
Oh, sorry, I misunderstood.
The part of interest of the example, like when you highlight the face of a person in a face recognition problem.
I mean,
that's the part of the face.
Yeah, there are tools, there are methods to do that.
Let me explain what he's saying. Suppose that you have a sensitive, very sensitive scenario, like cancer analysis. Is it better to try to understand what happens with an image, looking at parts of this image that were active, or also bringing from the database other cases that are similar? Yes. This is what he says.
Yeah, the training examples that are important.
Okay. All over my career, I have always worked with multi-example and things like that. And that's true. I have not talked about that in the talk, but I'm also pretty sure that we need to use several ways of explaining. So we need to use both information at the same time.
Okay. This goes in the direction of my question. So when you presented, I was trying to connect all of the parts. So I can imagine, and we can even write a project to explore this. I can imagine an explainability method that could select the hardest examples or the examples that are more important for the learning. Then we can try to swap parts of these elements to see the impact on the learning. So the feature part that you say that you can change the features, right? And we can even use with this learning layer-wise that you showed to see how you change the pathways. In this way, you can have the best of three worlds. You could understand the elements that help you You can understand the problem of learning the layers, and then you can see the parts of the elements that are helping the classification. I already have in mind one project. It's a very nice way of visualizing. And I have one question here in this direction from Jean. Do you know nice ways of selecting these elements that we say are more important? I mean, I can anticipate the brute force one. You can put the element if it helps the learning, so it decreases the learning curve. It's okay. If it does not change, this example is not that good. But other than brute force, like passing all of the examples in the summation of the cost function, do you know other cases or other ways of selecting the hard cases?
In fact, I have not dig too much in this direction. But you know, I'm working in a lab where we are using a lot of graphs, and I'm pretty sure that we could randomly select some example and do the brute force with them,
Okay.
and then create a kind of
Graph of
graph
dependencies,
proximity
and then
with,
you can
with,
find
the,
the
with the
hubs.
others, and
That's a good
probably
idea,
with some
yeah.
graph matrix we could
I got the
propagate
idea.
information.
So you randomly select a percentage of the data set, do brute force with them. These will be representatives of a graph, and then if the node becomes a hub, it's because that node is important. That's a nice idea as well.
It's like a control point. I have another question. If we think in a network as a physical process, we could imagine data be passing through lines with forces with different parameters. Do you know any solution based on scientific visualization in order to try to understand what is happening in the network? Because if we imagine that network as a physical network, we have this process, this physical process through those different lines.
Oh, you're asking if he knows any kind of explainability for physical neural networks.
For neural networks, but based on scientific.
Yeah, there are some physical based neural networks.
Yes.
PBMN.
Yes.
So do you know for physical based neural networks if there is any kind of attempt to explain?
No, but I think such kind of thing more complex would fit with Sankey diagrams and instead of using colors that depend on the classes, maybe kind of heat maps, or I do not know. But I would still go in a kind of graph-based representation with flows between the nodes.
Okay.
And colors on the edge that depends on the kind of information that go through.
I have another one here from Guilherme. Thank you for the excellent presentation. I'm new working with neural networks. I would like to know better about the data sets for training. What do you consider a good number of samples? And for image data set, the number of samples must be equal for each class. Yeah, he is wondering, based on your experience, what constitutes a good data set? This is a really hard question.
It's really hard because it will depend on the complexity of the problem. The more the problem is complex, the more data you need.
But I have another
and
question
the balance of other classes, I think, is something that is quite important.
I have another question for you. Based on your experience with visualization and explanations, do you have any tools that can help you to have a diverse training set?
There is this tool, FairViz, that goes in this direction, but it works only with tabular data. I do not know a tool, and I do not think that it could work with this tool that do something similar with image-based data, for example. Maybe it exists, but I do not know.
Okay, FairViz.
Yeah.
If you want to analyze a little bit about the diversity in the training.
Yeah.
Yeah, please take note of that, Maria.
Yes.
It's going to be useful for us.
Yeah.
One of the most important problems for us is it's not kind of having big data anymore. Andrew Ng is discussing this. It's much better if you can have a very good representative set, even if it's small. So trying to come up with something that analyzes diversity is something very important for us. I have another one here from Philip. Are there specific explainability methods for semantic segmentation? Do you know any?
I'm unable to give the name of a paper now, but I know at least 2 papers that are doing that. I can browse later.
So Philip, please send me an email, and then I will share with you the 2 recommended readings that Professor Romain will send me about this. Okay? Anybody in the audience would like to ask something?
Would you ask a question?
Please come here.
I'd like to ask a question about the network, the layer or layer. Do you know if there's any rule in work that do analysis by the diverse and the specific range for the layer? For example, for the first layer is more important a diverse number of kernels, and as we walk to the last layers, this kernel became more specific for some features. You know some works that
No, I do not know rules, and I have not tried with these analytics to get what is the best way to do that. But if I remember well, in the literature, most of the time, the more you go in depth in the network, the more number of filters you have.
And more specialized.
Often there are fewer filters at the beginning and more filters at the end. But maybe it's a belief. Okay, I do not know why we are doing that. Maybe it's just based on a belief, and maybe we could do the opposite. I have frankly no idea. I think it has been done this way because as you go deeper in the network, you have I've forgotten the word. You have pooling layers that are reducing the data size. So you can take more filters because of that.
Any other questions? Alexandre, please come here.
I'd just like to ask you about you have mentioned at the end of your presentation some limitations. For example, we don't only need to know the region, but why it's a dog or a cat like that. That's awesome. And have you an experience of using these techniques for in our society, in the court, for example? How far are we with these techniques to use this in our society in a more general way?
I do not know. I do not remember to have read papers that go in this direction, but I'm pretty sure that there are people at USP that works on that. Okay, but I have nothing to share. Yeah, I do not know. I even do not know real-world application of explainability in real world. I know tools that are used at Facebook, for example, but they are used
Do you
by
want to see
themselves.
real-world applications for explainability?
Yeah.
I can give you a lot. In our lab, we have like pretty much all of the applications we have with the industry. We need to understand.
Okay.
For instance, with Audio here, we have the hub of health and well-being. If we decide that a person has any problem related to diabetes, we need to show based on the heart rate, or based on the conductivity of the skin, or based on the blood, why we are taking that decision. So explainability is a pretty important piece for us. With Alexandre here in oil, if we decide that an injector is important to send more water to a particular well to produce more oil, we need to explain.
Okay. But do you publish these works?
Yeah.
Yeah. Okay.
Well, not in the Viva Bem yet because we just started, but with Alexandre we are trying to.
Yeah. And for example, in fake news, if you are saying that this image is fake in a court, for example, this is not really happening, and you need to know, okay, why you are saying that. So this is very convincing image.
Yeah.
And if you bring the image to the society, for example, everybody will believe that because it seems very real. But these algorithms can look for traces that, okay, this is why it's not real. There are some specific points there. But finding these points is very difficult, and showing to someone that's not in the scientific community or for a computer scientist, something like, it's very hard, right?
But we can think about hybrid methods. It can be a human that, thanks to an explanation, try to infer why. It means that the semantic that you are missing,
Yeah.
it can be provided by a human with its suppositions.
Not easy, right? Because if it's an algorithm that takes a decision, how can the human provide the explanation for the algorithm?
By his thinking, its suppositions.
Suppositions. Okay, yeah. The human can do some hypotheses and then try to prove it.
And then, thanks to this supposition, maybe we can add something over automatically that try to.
Yeah, this happens. So let me tell you an example. We had a project for 10 years to predict if a person was about to get blind. It's a complication of diabetes called diabetic retinopathy. So if the person develops this disease, there is a chance, probably 1 in 3, that this person can go blind in the future. So we got pictures of the retina using an equipment called retinoscope. So we took a picture and we analyzed the image. So the doctors, they already know the signs for the disease. So they know where it appears in terms of hemorrhages, microaneurysms, sites of fat, lipids, and other things. So they know that, and we train an algorithm to find those things. Then we show the image superimposed with the regions that we think it's fat, things that we think it's microaneurysms, and then the doctors come and confirm or discard the regions that we mark.
So this was using GradCam, right, for that?
We use it. One of the things that we used was GradCam, and this is now embedded in a device, a medical device. So this is where explainability is also important, and it goes with, as you said, with the expert. The expert needs to be present. Okay, so one last question. Yes? No? So Romain, once again, thanks a lot. Let's talk about collaborations. I have lots of ideas. And everyone in the audience, thank you as well for attending. Reminding everyone that tomorrow at 5 we have another talk about neuroscience and deep learning. So stay tuned. Thank you. Bye-bye.
Okay, thanks for the invitation.